And I think I'm recording. I have no idea. I've never done this on Zoom. Here we go. Okay, so the school is pushing us towards being more synchronous, trying to do things at the same time and at the right time, in the hopes that school is going to start up soon and that we'll already kind of be back in those good habits of checking in at certain times and maybe sleeping at certain times and things like that. I was talking to a student yesterday who said, yeah, I usually go to bed at 4 and get up at 2. And my daughter was in the room. She was like, I'm sure she was thinking, why can't I stay up till 4? No, I would go crazy. Okay. So anyway, I think the hope is just to kind of get us all on the same schedule again. Obviously trying to get as much of the face-to-face interaction as possible. And just kind of get back into the rhythm of things so that when school does start up, which we're pushing forward and hoping that it will, that we'll all be able to just kind of run right back into it again. So today we are starting with probability. Just so that you guys have an idea of what this will look like, we'll spend a couple of weeks on probability, 3 weeks probably, with the hope that by the time we finish probability, we'll be able to get back at school and finish the year with calculus for everybody. Both SLs, HLs, everybody gets to calculus. So that's kind of what the direction we're hoping to go in. We'll see how it goes. But anyway, let's go ahead and go straight into probability. Like I mentioned on the teams, I imagine that some of you have a lot of experience with this, and some of you have basically no knowledge of probability. So we're going to start with kind of the basics of what IB expects us to know and build onto that. So most of you, I think, are in Shenzhen right now. What would you say is the probability that it's going to rain tomorrow?
50.
50? Anybody else? See a couple of people talking. I think you're on mute though. Anybody want to say other than 50?
I think it's less because the weather forecast says it's going to be sunny.
Okay. All right. So some people went and looked at it. All right. That works. Iju, why'd you say 50?
Because last week it has been raining a lot, but from like 2 days ago it was still rain, but yesterday it was super sunny, but today it's a bit cold. It's like not certain.
Okay. So using your experience and saying that usually when it starts to get cold, it's because rain's coming or something like that. And some of you used your experience of looking on weather.com and found out that it's a 30% chance or whatever else. Okay. How about this? What is the probability that South Korea is going to win the gold medal in Taekwondo at the Summer Olympics? What do you think? South Korea, Taekwondo, gold medal. What's the chances? What's the probability?
90.
90 from a South Korean. There you go. Anybody else? What do you think, Alyssa?
Probably 90. I don't want to argue.
It doesn't want to argue with it. Okay. Erica, what do you think?
I'm also kind of afraid to argue. I mean,
that's a pretty bold statement to say a 90% probability that you're going to win the gold. What's your reasoning there, Yuju?
Because I don't think, like, a lot of country except for Korea has lots of good trainers for taekwondo because it's not a popular sport, but in Korea it's a very popular sport and it's a really common sport, so people have more access to not access people have more opportunities to learn more.
Okay, so Iju knows a little bit about South Korea and Taekwondo, obviously being from there. South Korea is one of the best, well, overall, looking at the history of the Olympics, they are the best. They're at the top of the medals in Taekwondo over the course of the last 100 years or something. So, I don't know if it's 90%, but a pretty good bet that they're going to do well. But obviously these probabilities, you're giving me these probabilities based off of experience. Some of you that didn't know anything about, maybe you're not from South Korea, or maybe you don't even care about the Olympics, probably would not have given a guess of 90%, because saying that I'm 90% certain I'm going to win the gold medal is a pretty big guess. So I guess the point I want to make is the probabilities that we're guessing right now as we try to deal with our experience and the things that we know, this is something called subjective probability. Okay. Now, subjective probability, there's nothing wrong with it, but what it is it's just us using our opinions, our experience, and creating a probability from that. Okay. And that's how probabilities worked for a long time is they would say, well, is it going to rain tomorrow? Well, sure, probably, or maybe, right? And those are kind of the guesses that they made based off of what they knew, or the patterns of weather, or the patterns of whatever else. So those are all examples of subjective probability. Okay. Now, obviously in a IB course, they're probably not going to be stressing subjective probability. They want to be a little bit more concrete. We want to be able to dig a little bit deeper. The real science of probability and statistics and things like that started actually in the 1500s is when the first real digging went into probabilities and stuff like that. It was actually an Italian guy that wanted to be able to gamble better. He thought that if he could come up with some mathematics to describe what was happening around the gambling table, that he would have an advantage over the other people at the table. And so he actually explored and created a lot of the rules of probability because he wanted to be able to make money. And that is where things come from a lot of time, is somebody wants to make money, and so they create something to be able to do that. And that's actually the foundations of probability. Now, obviously it's grown and we've done a lot more with statistics since then, but that was kind of the initial step into this realm of probabilities. So a couple of definitions other than subjective probability that we want to make sure that we understand. The first one is a trial. Okay, a trial is a single repeat of an experiment, right? So it's doing the thing once. That's a trial. Okay. The outcome is a possible result of an experiment. And so when we say, what are the outcomes? If you're going to roll a 6-sided dice, what are the outcomes? Well, the outcomes are 1, 2, 3, 4, 5, or 6. Those are the possible results of our experiment of rolling the die. Okay. The third one is an event. So an event is a singular outcome. So when I roll the die, there are 6 possible outcomes, but the one that comes out is an event. And so if I roll a 4, then the event is I got a 4. Okay. These are all very similar, but we need to make sure that when we read a question, because applications has so many of these word problems and things, Rosie's trying to get in. They have so many word problems. We want to make sure that we understand the terms that they're putting forward. The last definition that we want to make sure to get from the get-go is sample space. And a sample space is the list of all the possible outcomes. Welcome, Rosie. We're just doing some definitions to get started. Okay, so sample space is just a way that we can list every single possible outcome. Now with a single die, it's easy. 1, 2, 3, 4, 5, 6. But as soon as you roll 2 dice, you now could have a 1 and a 1, or a 1 and a 2, or a 2 and a 1, or a 1 and a 3. And obviously I could keep going for a while because there's 36 different ways that the dice could come out. And so we want to be able to come up with different ways of writing our sample space, or what are the possible ways that this could end up? What are the possible outcomes? And so as we go through this the next few days, that's one of the things we'll talk about is how can we represent a sample space, and then how can we use that to determine probabilities. Okay. Any questions before we go forward? I think that's all pretty basic, but wanted to make sure we had that. Okay. All right, I'm going to show you an app that is on Google. It's a really snazzy app. Let me see if I can share my screen with you here. This app allows you to virtually roll dice. Okay. And that is not what I wanted. Can everybody see that screen there with the 2 blue dice on it?
Yeah.
Is that showing up for everybody? Okay. So this, I'm going to have you do an experiment after I sign off with you today. You'll be using the 12-sided die, which is this one right here. And so the red one is the 12-sided. You can get rid of the dice just by clicking on it, and then they just kind of go away. But right now, we're going to deal with 2 6-sided dice. Okay, now every time you click on the die, not just kidding, not when you click on the die, when you click on roll, it's going to re-roll the dice for you. Okay, now if you want to do this, when you do your experiment at home, if you want to do it with real dice, that's fine. But I expect that not many of you have a 12-sided dice. I know if you play Dungeons and Dragons or something like that, you might have a 12-sided die, but otherwise you probably don't. So you can use this one just as a virtual rolling. Okay, so here's what we're going to do. We talked about subjective probability, but I want to talk about 2 other types of probability. One of them is theoretical probability, and the other is experimental probability. Okay, so let's talk about this. If I have 2 dice and I'm going to roll them, from your understanding, what is the probability that I'm going to roll doubles? Okay, I want you just to think about that for just a minute. If you want to write something down on the paper to try to figure out, that's fine. I'm going to give you 1 minute. I'm not going to talk. And I want you to think about what is the probability that you're going to roll doubles. Okay, go for 1 minute. And then I might call on some of you friends. All right. Lucian, what do you think, sir? What's the probability I'm going to roll doubles?
1 in 36.
1 in 36. Okay. I'll come back to you in a second. You can give me your reasoning. Let's see. Rosie, what do you think, friend?
Oh,
Isn't it like does the doubles mean like 2 1s and 2 2s like that?
Yep. 2 dice being the same. Exactly.
Isn't it then like 1 and 6 times?
1 and 6. Okay. Anybody have something different than 1 and 6 or 1 and 36? Jinwoo? What do you think?
Since it's a dice that has like 6 numbers and there's 2, so you can get like a total of 36, and you can get a total of doubles with 6. So 6 divided by 36, which is 0.16. So you have 16% of rolling, or 17% of rolling a double dice.
Okay. I believe that's the same that Rosie said, 1 and 6. 6 over 36, if you reduce it, divide both sides by 6, it should reduce to 1 over 6. I lost Lucian. I guess he'll come back. All right. So, yeah, there's a couple of ways to think about the theoretical probability here, right? One is to do what Jinwoo was saying, is he said, well, let me just think about how many different possibilities there are, right? There's a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, all the way to 1 and 6. Then there could be a 2 and a 1, a 2 and a 2, and write out all the possibilities, which would give you 36 possibilities. And then if you look at that sample space, all those possibilities, you can count how many of them have doubles. A 1 and a 1, a 2 and a 2, 3 and 3, all the way to 6 and 6. So there's 6 ways to get doubles out of those 36 possibilities. So 6 over 36. Another way to think about it would be this. When I roll the first die, it doesn't matter what that first die is, right? What matters is, will the second die match it? So no matter what that first die is, what's the probability that the second one is going to match the first one? One in 6. That's right. 1 every 6, because there's 6 possible numbers on that second die, and one of them will match whatever it is showing on that first die. And so there's different ways to think about these theoretical possibilities. Now, the way to make sure that you don't mess up with any of the logic is, of course, just to write everything out. But that can get really annoying when you have 36 possibilities or 100 possibilities or 1,427 possibilities, right? And so we will be exploring different ways to come up with the theoretic probabilities. In this case, the theoretic probability is 1 over 6 for the various reasons that we've talked about, okay? Lucian mentioned 1 over 36. That's the probability of getting a specific pair of doubles. Like the probability of getting 2 1s would be 1 out of 36. Probability of getting 2 2s is 1 out of 36. Okay, so good. What I want to do now is I want us to look at this die rolling sequence. And we're going to do an experimental probability, okay? Which means we're actually going to try it out and see what happens, okay? And I want you to look. I've put together something that is not here anymore. Let's see. So I put together a spreadsheet where we're going to put this data. There we go. Okay, so we're going to have this spreadsheet going, and then we're also going to be rolling the dice, okay? Can you see both the spreadsheet and the dice now? Can everybody see that? Should be a spreadsheet on the right side of the screen and the dice on the left-hand side. Yes?
Yeah, we can see it.
Okay, awesome. So what's going to happen is we're going to roll these dice several times. And what's going to happen is I'm going to keep track of how many successes we get, which means that it's a double, and how many failures we get, which is not getting doubles. All right, so as we roll, okay, so the first time we didn't get doubles, so that's going to be a 0. Okay, now there should be here a graph, but it looks like my graph has disappeared. So what we're going to do is we're going to plot it in here because I want us to see what the experimental probability looks like as time progresses. Okay, so for the experimental probability, that's the right column over here. Spreadsheets, Excel is really, really cool. What it does is it's going to allow us to calculate the experimental probability, which is how many successes we've had divided by the number of trials we've had. And we're going to put this together into a scatter plot. And we're going to see what it looks like as time progresses. So after my first experiment here, I have a experimental probability of 0. According to what I just did, in one trial, I got 0 successes. All right, so I want us to watch the chart down there as we put in more trials. So as we roll it, okay, we get another failure. We get another failure. Hopefully we're going to get a success eventually here. Okay, the next one is a failure. So our experimental probability, does this mean I'm never going to get doubles? What do you guys think? Right now, my experimental probability says I got a 0 out of 5 chance of getting a double. Am I never going to get a double? What do you think?
No.
No? How about the next one? Is the next one more likely to be a double? Because I got no doubles 5 times in a row. Does that mean the next one's more likely?
No, it's less likely.
Less likely to be doubles?
As
No,
likely.
it's more likely. Yes, yes.
More likely.
What do you think?
As
More
likely.
likely.
Because not one event is interrelated to another.
Okay, so this is an important idea. This is an idea of independent events, right? When I roll the dice, do the dice know what was rolled before? No, the dice have no idea that I just rolled 5 non-doubles. So when I roll them again, does it make it more likely that it's going to be doubles?
No.
No. That is a very important idea of independent events. In fact, one of the things that I was going to share with you guys, there was actually in the early 1900s, there was a casino where they were playing the game of roulette. Do you guys know the game of roulette? It's the one with the spinning wheel that has the red and the black, and then the ball that goes in and bounces around, right? And then people try to guess whether it's going to be a certain number or red or black. Raise your hand if you know what I'm talking about. Okay, so almost everybody knows what I'm talking about with roulette. There was a situation where 15 times in a row, the ball landed on a black number. Do you know what happened? All of the gamblers in the casino crowded around and started putting their money on red. Why would they do that?
Because they thought that because so many events of black came out, they thought the next event would have to be red.
That's right. They were thinking that over the course of a certain amount of time, you should get half red and half black. So they thought, well, because there's so many blacks, that means it is more likely that I'm going to get a red. And after 15 blacks, they all put their money down on red. And you know what happened?
It went on black again.
It went on black again. And so what did they do?
They cried and lost their money.
They cried and lost their money. And then they put more money on the red. because they were more certain that the next one was going to be red. This is a true story. As it happened, it landed on black 28 times in a row. It wasn't cheating. It wasn't fake. It was probability. There is a 1 in like 60 million probability that you're going to get 28 blacks in a row. And yet it's possible. With all the roulette tables in all the world running 24/7, right? If you get 64 million of those spins, probability says one of them is going to get 28 blacks in a row. Somewhere else in the world, it's 1 in 60 million that you're going to get 28 reds in a row, right? But the point is that when we talk about probability, there's nothing guaranteed. It's all probable, right? And in these independent events, like with the ball on the roulette table, when you have independent events, just because something happened before has no effect on the next event. Now, after I said all that, I'm hoping that I don't get 27 non-doubles in a row. Where'd my die go? Let's see. This is what happens when you do a real experiment in class. It never works. I got another non-double. Come on. Feel like I'm at a craps table now. Come on, doubles. Oh, there we go. There was one. Okay, so what do we got now? I'm looking at my table here. So I got 2 more non-doubles. And then we got a double. And then we got another non-double. Okay, so we're looking at our table now. Let's see. Can't see the chart. Let me move it over. There you go. So all of a sudden, my probability, it was 0. Experimental probability was 0 because I got 0 doubles. And then all of a sudden, it jumps up to just over 12% because then I had 1 out of 8 that was a double. All right. And now the probability is going to go down again. Let's do a couple more. So not a double. There's a double. Let's put those in. Not a double. Double. See, my graph's going to change as we go. I want us to be able to look at the graph. So not a double, not a double, not a double, not a double, not a double. I got 6 not doubles. There's one. So 1, 2, 3, 4, 5, 6, and then there's another double. Okay. What are you seeing as time progresses? Here, let me move this over so you can see it. I want you to think about what we're seeing in that graph as we do more and more experiments. Take just a minute to think about it. I'm going to put about 10 more of these in and see what we get. All right, I think that's good enough for what I'm trying to accomplish here. What do you see in that graph as time progresses? I'll delete all the last ones so that it's not. All right. Oh, where'd my graph go? Oh, there we go. Make that bigger. Anybody, what are you seeing here? What do you think? What's happening in this graph?
It gets closer to the theoretical probability as the sample size increases.
All right. Can everybody see that happening? Right? We started off with some 0 experimental probabilities, right, down here. And then as time progressed, we got a little bit closer. Jinwoo, you gave us the number, right? It was about
0.167.
167, so 16 to 17%, which should be right around here, right? And you can see as time progresses, it starts to get closer to oscillating around that number, okay? And that's how we can sort of prove an experimental probability. We said we believe the experimental probability is about 16%, 17%. If we run more and more and more trials, it should oscillate around that 16 to 17%. Yes, some weird things will happen. Just like in the beginning, I got 7 in a row that were not doubles. Weird things happen. However, over time, if we look at the big picture, then we should be able to start to see that 16 to 17% coming out. Okay? The key is getting enough trials. Just like when we did statistics, remember we talked about statistics, we talked about bias, we talked about how to get better results. And one of the things was the more people that you asked, the better your results were, right? And so that's one of the things that we want to be able to get across as we're talking about probability here. Okay? Any questions so far? Everybody okay? Okay, so I wanted to make sure to get these concepts across because we want to know the difference between our subjective probability, our theoretical, and our experimental. Because being an applications course, it's very likely that they're going to give you some data on an exam and ask you, does the experimental probability match with the theoretical probability? And then you'd have to be able to go through and kind of decide whether it ends up giving you the same thing. And we'll talk more about that kind of as time goes over the next couple of weeks. Okay. How about this? Let me give you a couple and see if you guys can come up with the theoretical probabilities. Okay. The first one, consider an 8-sided die. Okay, so it's a die that has 8 equal sides. 1, 2, 3, 4, 5, 6, 7, 8. What is the probability that when you roll it, it will give you a prime number? Eight-sided die, what's the probability it will give you a prime number?
One.
Here, 1/2. Anybody else?
Round 2.
See some nodding. Okay. What are our prime numbers there?
2, 3, 5, 7.
2, 3, 5, 7. So there's 4 of them out of 8 possibilities, assuming that all the sides are the same and it's a fair dice. 4 out of 8, which reduces to 1/2. Very good. How about this one? What is the probability that